Hi guys, be with you in a
Good
moment.
afternoon. How you doing?
How you doing, guys? Doing okay. Give me a moment here. I gotta start my cell phone. Okay, hope everyone's doing okay.
Doing good.
All right, everything doing okay on this end. I do have a couple things, and I wonder if when you got time, you can give me some feedback on this online thing. I just been assigned a course for the summer. This course 130, which is going to be totally online, and I could really use some feedback from you guys so I can make this a little bit better. I realize that a couple things. My computer is not the best in the world. I do have a new one coming up. Should be delivered to me Wednesday or Thursday, and hopefully uh, my recordings and my sound and audio is a little bit better. So kind of updated. It's about 6, 7, 8 years old. So that aspect I hope to get better. So if you want to take a few minutes to shoot me an email through Canvas, tell me, give me some suggestions on how I could make this a little bit better. You guys are like the guinea pigs. We kind of switched over midstream, and so yeah, I would really appreciate any information you have. Okay, um, let us proceed then. We're moving along. This new chapter is called Stoichiometry. Okay, big old fancy name, Stoichiometry. But we have been doing it a little bit all along. When we were balancing equations, I mentioned to you, hey, make sure, take a look at the reactants and look at the coefficient in front after we balance it. We can see there's a ratio of 2 to 1, 1 to 1, and so forth. And that's where this whole chapter comes into play. We're going to combine all that information and start looking at reactions and actually start calculating. If I start with X amount of A and X amount of B, how much a product I'm going to make. And this is done in the real world. I did in the real world, regardless if you do a reaction in the bench, in the lab, and you're doing a few milligrams. Yeah, in the real world, when you're making tons of this compound, the same reaction proceeds, and we can calculate and use it for determining, predicting how much product you get. So this is what this whole chapter is about, called stoichiometry. Okay, now we went through balancing chemical equations, and this first equation that you see up here is nitrous oxide reacting with uh, oxygen to give us NO2. And we're balanced. We have 2 nitrogens as a reactant, and we have 2 nitrogens as a product. So we got 2 there, 2 there. We have a total of 4 oxygens as a reactant, and we have a total of 4 as a product. Okay. Now the relationship, this what's called the stoichiometric relationship, is that coefficient. There's 2 of NOs required for every 1 molecule of oxygen. Okay. There's not a number in front of oxygen gas, but it's understood there's a 1 there. Okay, so that relationship is 2 to 1. Okay, So we can say that I require 2 molecules of NO for every 1 molecule of oxygen, or going back to using moles, if I have 2 moles of NO, I need 1 mole of oxygen. Okay, that's a relationship. Now, not only that, we can look at the product. We can see that every 2 moles of NO, we're going to make 2 moles of NO2. So that ratio is a 2 to 2 or 1 to 1. Okay, if we compare it with oxygen, you can see that that ratio is a 1 to 2 from oxygen over to NO2. Okay. Now, another example would be we're reacting nitrogen N2 with hydrogen gas to give us ammonia. In this relationship, after we balance the chemical equation, the crucial part is you got to make sure you have it balanced. If it's not balanced, then the relationship is not true. So we have that 1 mole. Remember 1 mole, 6.02 times 10 to the 23rd molecules. That number of nitrogen molecules require 3 moles of hydrogen gas. Okay? And so if we were to have, say, 100 moles of N2, what does that tell you about how much hydrogen you need? You need 300 of hydrogen. Okay? Because that stoichiometric relationship is 1 through 3. And vice versa. If I go the opposite direction, I need 1/3 less of N2 compared to hydrogen. All right. So the coefficients from the balanced chemical equation gives us those mole ratios. Now, think back, way back when we were talking about conversion of units, I emphasized the ratios. Okay. Why? Because now we're here. And I said those ratios, whatever it is, miles per hour, dollars per hour, I can write them 1 or 2 ways. So the ratio between nitrogen and hydrogen in the previous examples is I can write 1 nitrogen in the denominator, 3 hydrogens in the numerator, or invert it. 3 hydrogens in the numerator and 1 in the nitrogen. That is that ratio. And which one we use depends on the question being asked or what we're trying to calculate, keeping track of your units. Okay. So here we got this particular reaction, okay, where we have iron 3 oxide requires 3 molecules. 1 molecule or 1 mole of iron 3 oxide requires 3 moles of carbon monoxide to give us 2 moles of hydrogen and 3 moles of carbon dioxide. So the relationship between the 2 reactants, between here, and here, is a 1 to 3. And so we can write it at ratio, like I circled it, with the iron 3 oxide in the numerator and carbon monoxide in the bottom. Or we can invert it, okay? Depending on what we're looking for, okay? Also, you're not limited just through the reactants. Hold on, I made one more. If you look at the ratio between carbon monoxide and iron, that's a 3 to 2. If we look at the relationship between carbon monoxide and carbon dioxide, that's a 3 to 3 or 1 to 1, okay? And so you're not just talking about reactants, you can look at the relationship between reactants and products and between even the products themselves. Because if you look at the products, the relationship is 2 irons for every 3 carbon dioxide, okay? And so we could write the relationship between iron right there and carbon monoxide right there. And that ratio is a 2 to 3 ratio, 2 iron to 1 carbon monoxide. And we can write it like that or invert it, okay? Now, when you look at these problems coming up, let me erase some of that. They're asking you, let's look at question number 1. It says, how many moles of iron can be formed from 10.2 moles of carbon monoxide, okay? And so they're asking to look at iron and carbon monoxide. So what we're concerned about is iron and carbon monoxide, that relationship only, okay? That relationship only. We don't worry about everything else because the question is just asking what's going on between carbon monoxide and iron, okay? So what I see here is a 3 to 2 ratio, okay, between carbon monoxide and iron. And so therefore, the question says, how many moles of iron do I need if I start off with 10.2 moles of carbon monoxide? Iron has to be in the numerator, just like the conversion factors we were doing. Whatever you're looking for is going to be in the numerator with respect to how you set that problem up. So let's set it up, okay? Oh, get all these ratios there. Okay, so you can see as we write down what we have, what we're given, which is 10.2 moles of carbon monoxide. And now we insert that ratio of 2 to 3 where iron is in the numerator because that is what we're looking for, and carbon monoxide is in the denominator. You see how carbon monoxide units cancel, leaving us with the units of iron. Now, simply do the math, 10.2 times 2 divided by 3, giving us 6.8 moles of iron, okay? So if you start off with 10.2 moles of carbon monoxide, you should make 6.8 moles of iron, is all that equation's telling you. It's always telling you at this point, okay? Now, once we were in moles, remember I mentioned that when we want to go from A to B, and this is what we're doing. We're going from A to B, A being iron, B being carbon monoxide. Once we have to go through moles to get from that point. That's our factor. That's our unit that everyone can relate to as far as reactants and products. Once we're at moles, right there, by now picking up the molar mass and or the atomic weight, we convert it to grams, and hence we have a weight, okay? So keep that in mind. Next question says, how many moles of iron 3 oxide? So that's what we're looking for. So our relationship is iron 3 oxide needed to form 17 moles of carbon dioxide. And so now the question pertains to only iron 3 oxide and carbon dioxide. That ratio says it's a 1 to 3, okay? And since we want to figure out how many moles of iron 3 oxide, the iron 3 oxide will be in the numerator, okay? Let me erase all that mess so we can see what the setup. And so you can see here that we got 17 moles of carbon dioxide. That ratio is a 1 to 3 between carbon dioxide and iron 3 oxide, okay? Our carbon dioxide cancels out unit-wise, leaving us with iron 3 oxide in the numerator. And now you simply do the math. So 17 divided by 3, giving you 5.7. Excuse me. Keeping track of your sig figs. Don't forget the sig figs, because we got 2 sig figs there. These numbers, 1 and 3, obviously are exact numbers, and therefore don't play a factor in sig figs. So our answer should have 2 sig figs. Okay. All right. Let's do a couple more. So you may be given an equation here, and you kind of have to balance it. This is where you take some of the work problems in the worksheet and practice. A lot of balancing is in mathematics. Like mathematics, you require a little practice. But you can see I got a three. I got SO2, sulfur dioxide, reacting with oxygen to give us sulfur trioxide. So I gotta find a common factor here, you know. So I can say let's put a 2 there, which now gives me 6 oxygens from sulfur trioxide. All right, and now I got 4 on the left side. So I come back and I put a 2 there in front of sulfur dioxide. So my oxygens at this point are balanced on both sides. And guess what? My sulfur also is balanced. So I got 2 sulfur as a reactant, 2 sulfurs as a product, 6 oxygens as a reactant total, and 6 as a product, sulfur trioxide. Okay, and now my relationship is a 2 to 1 with respect to sulfur dioxide and oxygen. From sulfur dioxide to sulfur trioxide, that ratio is 2 to 2, okay, or 1 to 1. And the relationship between oxygen and sulfur trioxide is a 1 to 2. Okay, so I got three ratios here: ratio between the reactants, ratio between one of the reactants and the product, and the other reactant and the product. So I got 3 relationships here, ratios to be familiar with. Why? Because the problem can take you to either one of them. And so here the problem says how many moles of sulfur trioxide. So we wanted to calculate how much product we're making. Okay. And so that tells us sulfur trioxide, as far as that mole ratio, is going to be in the numerator. And will form if we start off with 0.165 moles of oxygen. Okay, so we're only looking at the interaction between oxygen and sulfur trioxide, which is a ratio of 1 to 2. Okay, so, oh, we went too far. So we can set it up. We write down what we're given, which is this. Okay, this comes from the balanced chemical equation because we're looking for sulfur trioxide. It's in the numerator. Notice that my oxygens unit-wise cancel, leaving us with 0.330 moles. Okay, and it kind of makes sense. So makes sense, doesn't it? Because from the ratio it's a 1 to 2. And so whatever number I start off with oxygen, I should get twice the amount of sulfur trioxide. And sure enough, 0.165 times 2 is 0.330. Okay. All right. Oh. Second question is how many moles of sulfur dioxide, SO2, are needed to make 0.042 moles of sulfur trioxide? So here's an example of I'm trying to make an X amount of sulfur trioxide. How much sulfur dioxide do I need to start off with? Whoa, what happened? Oh, one moment. Something happened. Bear with me. Okay, here we go. I may have hit the wrong button. I don't know. Anyway, we're looking at this one here, and they're asking us how many moles of SO2, okay, are needed to make 0.042 moles of sulfur trioxide. So we're only concerned about sulfur trioxide and sulfur dioxide. And that relationship, you can see it's a 2 to 2 or a 1 to 1, okay? 1 to 1 relationship. So we can set up the problem, and guess what? It's the same value. Why? Because in the balanced chemical equation, it's a 2 to 2 relationship or a 1 to 1. So if I need to make 0.042 moles of sulfur trioxide, I need 0.042 moles of sulfur dioxide. Okay. Now, the important part about all these calculations is that you must have a balanced chemical equation. Without that balanced chemical equation, okay, all these calculations are incorrect. And this balanced chemical equation, whether I'm making 0.042 moles of sulfur dioxide or whether I'm making 10 billion moles of sulfur dioxide, that same relationship, the same relationship is true. Okay. All right. And so this flow chart kind of breaks it down for you so you can see. Sometimes you are given grams in the problem. Okay, right there. Well, remember, when I have a weight, a mass, I need to get into moles. So I must get into moles. And the way to do that is I need the molar mass. I need the molar mass or the atomic weight if that's an element. Okay. When I take grams and divide it by the molar mass, I get moles. This mole ratio comes from the balanced chemical equation, and that relates reactants and products with each other. Okay. And so once you have that from the balanced chemical equation, you can again then determine the moles of what you're looking for, what you're trying to find. Once you have that and you have the molar mass and or atomic weight of that compound, you can then calculate the grams. Okay? And so the point being, to get from A to B, regardless of what it is, you must go through moles. Okay? You got to have moles to get through all that, to point A to point B. And to get to moles, you need the molar mass. Okay? To get to moles. And once you have moles, you need the molar mass again to get back to grams. Because again, in the lab, we don't have a balance that weighs out in moles. We have a balance that weighs out in grams. So we don't work with moles in the lab. We work with grams, but we calculate moles. Okay, so this flow chart kind of summarizes the whole thing of going from mass to mass. Mass of what you're given, mass of what you're looking for. Okay, so in this example here, we have iron to oxide reacting with aluminum to give us iron and aluminum oxide. Okay, this is a specific type of compound. A reaction is the same. Does this look like this single replacement reaction? Sure does, because we replace the iron in iron oxide with aluminum. And if you look at the activity series, compare iron and aluminum, you'll find that aluminum is a lot more reactive than iron. And then the next question you ask, well, is aluminum in compound form? No, it's not. It is an elemental form. so therefore reaction proceeds. Okay, so here's a single replacement reaction. And sometimes that type of problem can come up. They ask you, write the reaction of iron to oxide with aluminum. Well, you have to find out first, is it going to react? Then you got to make sure you write the right formula for iron to oxide. I know it's iron 2. Why? Because oxide is a -2. That means iron must be a +2 here. Okay. So once you write the reaction, then you got to balance it out. And here we have a balanced chemical reaction. It takes 3 iron 2 oxides for every 2 aluminum, every 2 moles. 3 iron 3 oxides will produce 3 irons. 3 iron 2 oxides will produce 1 mole of aluminum hydroxide. Okay? And that's the relationship between one of the reactants and 2 products. You do the same thing with aluminum. 2 aluminums, oh my goodness, 2 aluminums require 1 iron. And 2 aluminums will give us 1 mole of aluminum oxide. Okay? All right. And let me erase this. All right. So, they're asking you here in the question, calculate the mass of iron 2 oxide needed to react completely with 5.5 grams of aluminum. Okay, so what we're concerned about is simply the iron 2 oxide and the aluminum. Okay, you want to figure out, if I start off with 5.5 grams of aluminum, how much iron 2 oxide do I need so it can react completely? And note the ratio between the 2 reactants, 3:2. Okay, so you keep that in mind. And the second part of the question, says, we're going to go through all this. Calculate the mass of aluminum oxide. So let me erase this. In this scenario, calculate the mass of aluminum oxide, which is one of the products, produced when we have 10.25 grams of aluminum, which is one of the reactants. Okay, so we're only concerned about that relationship, aluminum to aluminum oxide, and that relationship ratio is a 2 to 1, 2 moles of aluminum to 1 aluminum oxide. So we make note of that. Okay. So let's do the 5.5 grams of aluminum. There, the reaction again is given to you on top. So that's, write down what you're given. Okay. Well, remember, we need to get to moles because we're starting off with grams of aluminum. At 26.98 grams per mole, that is the atomic weight of aluminum, which you can find from the periodic table. Okay. So, and follow your units along. Look at my grams of aluminum, cancel. So at this point, if I do the math, I end up with moles of aluminum. Okay. From the relationship in the balanced chemical equation, it's a 2 to 1 ratio. 2 iron oxides, iron 2 oxide to, 3 iron 2 oxides per 2 aluminums. Note the units. Follow along, cancel them off. At this point, I can calculate the moles of iron 2 oxide. Okay. And finally, because the problem asks for grams, okay, we go back and figure out the molar mass of of iron 2 oxide. Okay. Molar mass, look up the atomic weight of iron, atomic weight of oxygen, and it has a molar mass of 71.85 grams. Again, following the units, all the units have properly been canceling out, leaving me with units of grams per iron 2 oxide, then tells you I set the problem up correctly, okay? Now it's a matter of plugging in the numbers in the calculator, and you should end up with 22.2 grams of iron 2 oxide. So what that means is, if I start off with 5.55 grams of aluminum, okay, I need 22.2 grams of iron 2 oxide for this reaction to proceed as written. Okay, second part of the equation says you're given 11.25 grams of aluminum, okay? And so we want to convert that to moles, again, like we did in the first example. But in this case, we're going to use a different ratio. Why? Because the question asks, how much aluminum oxide am I going to make? So we're just concerned about the aluminum and the aluminum oxide, okay? Also, keeping track, following your units, notice grams of aluminum cancel, moles of aluminum cancel. At this point, you are at moles of aluminum oxide, okay? Then we need the molar mass of aluminum oxide, because finally, unit-wise, we're at what we're looking for, and that is grams of aluminum oxide. Now you just simply put the numbers in, calculate it, keep track of your sig figs, and that means that if I start off with 10.25 grams of aluminum, okay, I should make 19.35 grams of aluminum oxide. Okay. This flow chart kind of puts it all together for you. I gave you one earlier, but this one also incorporates gases at STP. Remember, we talked about those. At STP, standard temperature and pressure, a 1 mole of a gas occupies a volume of 22.4 liters per mole, okay? Now, what this means is that we can go from here all the way across what we were looking for right now, what we were doing, from grams given all the way to grams, what we're searching for, okay? But notice that we have to go through moles. This mole ratio comes from the balanced chemical equation, okay? Moles given here, we got to calculate that because we need the molar mass or the atomic weight if it's an element. And once we have that, we use the mole ratio to find the moles that we're looking for, and then its molar mass then gives us the grams that we finally want to calculate. Okay. Now, sometimes we can go from here, grams given, all the way down to volume of gas in that direction. Okay. If you're at STP, remember that. We can go from grams given down here to the left to calculate how many moles of gas I need of a compound that is gas at STP, okay? But you're not limited in that direction. You can go, if you need to find out how much an X amount of grams you need to make, you can go back to where the beginning. So it's getting messy there. So the point of that graph is you can go in every direction, starting from the bottom left corner all the way to the top right corner, bottom right corner all the way to the top left or the top right, or you can go from gas all the way here to the gas, okay? So if you study this flow chart, I think the problems that we have given you with respect to the homework and with respect to the worksheet, you hopefully should not have a problem trying to get from point A to point B. Okay. So here's a reaction. They're asking you write and balance the reaction of hydrochloric acid with solid cobalt. They're telling you what cobalt's going to end up as far as an ion. It's telling you that it's going to end up with a +2, because cobalt is one of those metals that it could have a variety of oxidation numbers. Okay, so problems like this, they have to tell you what state is it going to be, unless you're dealing with the sweet 16, which we know what the oxidation number would be at all times. Okay, so we write down the equation, okay, where we have hydrochloric acid reacting with cobalt to give us cobalt 2 chloride and hydrogen gas. Now this reaction proceeds. If we look at the activity series, we will find that cobalt is a lot more reactive than hydrogen. Hydrogen, you'll see in activity series is just given the letter H. So cobalt is a lot more reactive than hydrogen, okay? Hydrogen plus proton, that is the compound state of hydrogen. So the next question is, of the most reactive element, is it in a compound state? And the answer is no. Cobalt is elemental, so the reaction proceeds. Okay. They told you that cobalt has a +2, so you write the ions with a +2, and we know that the chlorides have a -1. Remember, they're in group 7, and therefore I need 2 of them to balance out the +2 of the cobalt. Okay. So then hydrogen gas is given H2. So anytime hydrochloric acid reacts with a metal, the product you always get is hydrogen. That's the elemental form of hydrogen from the activity series. Okay. And let me see. Now we balance it, and it is 2 hydrogens to 1 cobalt to give us 1 cobalt chloride and 1 hydrogen gas. Okay. Now they're asking you a question here. How many liters of gas at STP will form if you have 5 grams of cobalt reacts? All right. And so what we're concerned about is how many liters of gas, which would be the hydrogen gas, will form if we start off with 5 grams of cobalt. And so we're only concerned about these 2 here. Plus, we're at STP. Being STP, we can use that relationship, 22.4 liters per mole. Okay? And so we set the problem up. We write down what we're given. We're given 5 grams of cobalt. Okay? Okay. We need to convert the cobalt to moles. Remember, we can't go anywhere without converting to moles. Okay? And so we look at the atomic weight of cobalt, which is 58.93 grams. Okay? Then we look at the relationship from the balanced chemical equation of cobalt and hydrogen. Notice, keeping track of my units here. I got grams cobalt canceling, moles of cobalt canceling. Unit-wise, I'm now where I'm looking for moles of hydrogen. Okay. Then, because we are at STP, okay, we can use that relationship that takes us directly into liters, 22.4 liters per mole for hydrogen, because we are at STP and only at STP. If that STP was not that not given in the problem, This is about as far as we can go. We can take it to grams, but we couldn't figure out, calculate the liters. Okay, so we end up with 1.9 liters of hydrogen gas. If we start off with 5 grams of cobalt, and we are at an STP temperature, 0 degrees 1 atmosphere, we should make almost 2 liters of hydrogen gas for that reaction. Okay. Now, let me erase some of this here. We got too much stuff going on. Another example would be if 2.374 liters of hydrogen gas were formed, how many grams of hydrochloric acid reacted at STP? Okay, so now they're telling you how much hydrogen gas was formed, was created. So they want you to back calculate to figure out how much hydrochloric acid actually reacted. Okay? That's what they're telling you there. So from the balance chemical equation, we see that relationship. I got 2 hydrochloric acids per 2 moles of hydrochloric acid per 1 mole of hydrogen gas. Okay. Plus, we're still at STP. So keep in the back of your mind that maybe the 24.4 liter per mole could be used here. Okay. So we write down what we're given. 2.374 liters of hydrogen gas. Okay. Since we're at STP, based on the problem, we can use this relationship. 1 mole per 22.4 liters. Okay. We go to the balanced chemical equation, which tells us there's 2 moles for every mole of hydrogen. That's from the balanced chemical equation, which then will, keeping track of my units, will give me the moles of hydrochloric acid. Okay, so we're almost there. We're still at STP, and so I can go directly to volume because, well, I can do a couple of things here. If the question asks for how many liters of hydrochloric acid reacted, we can use the 22.4 relationship. But the question asks for how many grams. Okay, so therefore I need the molar mass. And again, looking at my units, I end up with grams of hydrochloric acid. Okay, and that represents 7.2 grams of hydrochloric acid. And notice something here. That digit has 3 sig figs. We started off with 4 sig figs. Okay, so why do we have 3 sig figs? Because remember I said that molar masses we don't use. Okay, so we don't worry about those. We don't worry about molar mass there. These numbers are exact 2 and 1, but the 22.4 liters per mole is a measurement. It's not an exact. And there are 3 sig figs there. So our answer with respect to sig figs is governed by the 22.4. Hence, we have 3 sig figs as the answer. Okay. All right. So here we go with another example. How many liters? Okay. Well, they give you the word. They give you the word problem. Hydrochloric acid plus oxygen gas produce chlorine gas and water vapor. Okay. So we got to write the reaction down. Hydrochloric acid plus oxygen gives us chlorine gas plus water. Then we balance it, okay? Which tells us we have 4 moles of hydrochloric acid for 1 mole of oxygen, 4 moles for 2 moles of chlorine, 4 moles of hydrochloric acid for 2 moles of water, okay? 1 mole of oxygen per 2 moles of chlorine, 1 mole of oxygen per 2 moles of water. So I always like to find the relationship of all the reactants and products involved. And even between products, it's a 2 to 2 or 1 to 1, okay? So here, they're asking you how many liters of chlorine can be formed if you have 3 liters of oxygen at STP. So how many moles of chlorine can be formed if it reacts with 3 liters of oxygen? So we're only concerned about these two, oxygen and chlorine. Okay. Plus, we're at STP. So that 22.4 liters per mole could be used here. Okay, let's set it up. Write down what we're given. We got 3 liters of oxygen. Okay, well, sure enough, we need the 22.4 liter per mole because that puts us into moles of oxygen because we're at STP. Then the mole ratio between chlorine and oxygen is 2 to 1. That comes from the balanced chemical equation, 2 to 1. Okay. Oh, sorry about that. Here we go. Push the wrong button. Keeping track of my units, you can see things cancel out, leaving us with moles of chlorine. Okay. The question says we want to know how many liters of chlorine gas. So since we're at moles of chlorine, we can use that relationship again of 22.4 liters. And we end up with 6.00 liters of chlorine. Okay. You can probably figure out that based on the balanced chemical equation and based on the fact that we're at STP, we just need the stoichiometric relationship between the two. Why? Notice this, that and that cancel out. So when you are at STP and you're dealing with gases, you don't need to worry about the 22.4 liters per mole because they cancel out eventually. All you need is a stoichiometric relationship between the two reactants, but only if you're dealing with gases and only if you're at STP. Okay. All right. This is a relatively short chapter, so it won't take long. I want you to try these at home. Okay. The problem says if carbon reacts with oxygen to form carbon monoxide, all right, says how many liters of carbon monoxide at STP can be made from 15 grams of carbon and 20 liters of oxygen gas. All right. So that happens, you should end up with 28.0 liters of carbon monoxide and 40 liters of carbon monoxide for the second question. 28 for the first, 40 for the second. Okay. This would be a good problem if you come up with an answer that doesn't match that, send me an email, we can go over it, or don't forget I'm on Zoom here Monday and Wednesdays and Saturday, and for office time. To date, I've had 1 student. Okay, so I'm assuming everything's going okay. All right, kind of overview of the calculations. Okay, step number 1, we take elements, and from the elements, when they become ions or compounds, eventually either covalent or ionic, we make compounds. So we take the elements to make compounds. Okay, from the compounds, then we write reactions of reactants combining to have a reaction, and then we balance it. We got to balance it. From the balanced chemical reactions, we have that stoichiometric ratio between reactants and products. Okay, and based on those ratios, we can do calculation of reactants or products in terms of either moles, grams, or volume, liter. Okay, so that flow chart summarizes this whole stoichiometric relationship and how to get from point A to point B. And the thing to remember is that we need to get through moles, okay? Converting anything to moles so we can compare apples to oranges, okay? And that's it. If you got that, remember, if I start with grams, I divide by the molar mass to give me moles. If I have moles, I multiply by the molar mass to give me grams. Okay, and the yellow parts down here, only if you are at STP where that relationship is true. 0 degrees, 1 atmosphere. If you're not in STP, you can't calculate. Okay. That being said, guess what? Congratulations. We just knocked out another chapter. Okay. Now the next chapter, 14, is a little more extensive. We'll probably be taking the whole time. It's called Intermolecular Forces. That one deals with molecules interacting with each other, but how they do that. And that has to do a lot with polarity. So you go back and refresh your memory about polar molecules, okay? Because when we talk about IMF, chapter 14, there's only 4 types of interactions. And those are driven by the polarity of the molecule. So refresh your memory on that, okay? It's polarity didn't go away, it's coming back. And then 15, the last chapter, that one is fairly small. Those are solutions, nothing too big on that. But IMF takes a little more study. Okay. So other than that, that's all I have for chapter 13 today. Don't forget, you have the next exam. It should be open now. So don't forget to do it. If you haven't done so already, there's a time limit, 75 minutes, and it will shut off at 11:59. So